In previous lecture, I discussed chord vertex, chord edges, vertex chord and vertex connectivity. If by removal of a vertex the graph is disconnected, it's called as a chord vertex. If by removal of a edge the graph is disconnected, it's called as a chord edge. If by removal of set of vertex graph is disconnected, it's called as a vertex chord. And the minimum number of vertices in vertex chord called as vertex connectivity. Today I will discuss edge connectivity. We can also measure the connectivity of a connected graph in terms of minimum number of edges we need to remove to make this graph disconnected. If there is a chord edge, we can simply remove that. So edge connectivity will be 1, that chord edges. If there are no chord edges, we can remove multiple edges to make this graph disconnected, and it's called as a edge chord. In case of vertex, it's called as a vertex chord. In case of edges, it's called as a edge chord. And the minimum number of edges in edge chord called as edge connectivity, and edge connectivity can be denoted by this gamma of G. The minimum number of edges in an edge chord we can represent by gamma of G. Gamma of G equals to 0 if the graph is disconnected or it have a single vertex. Vertex connectivity lies between 0 and n minus 1 if n contains the number of vertices. Now let's see one example. Example 6. Find the edge connectivity of each of the graph in figure. I am using the previous figure what I discussed for vertex connectivity. Same figure. All figure have more than one vertex. So vertex connectivity is positive. Same as edge connectivity also positive. Now check for graph 1. In graph 1, CE is the chord edges, or you can say bridge. So by removal of CE, we can disconnect this graph. Hence, edge connectivity equals to 1. There is just one edge whose removal make this graph disconnect. Now check G2. In G2, vertex connectivity is 1. We can simply remove C and all its adjacent edge. So vertex connectivity is 1. But what is edge connectivity? To make this graph disconnect, we can remove BC, AC. Means we need to remove two edges, or we can remove CD, CF, or we can remove AB, BC. So B will be one part and rest all this thing will be one part. So at least we need to remove two edges to make this graph disconnected. Hence edge connectivity is 2, whereas vertex connectivity is 1. Next check G3. To make G3 disconnected, we can remove BC, GF. So we are removing two edges to make this graph disconnected. That's why edge connectivity is 2. You can remove CD, FE, or simply can remove AB, AG. Next graph G4. To make it disconnect, we need to remove 3 edges. You can remove AB, AG, AF. So A will be one part, rest will be another part. Or you can remove AF, GF and BC. So this AGB will be one connected component, whereas CDFE will be another connected component. So minimum 3 edges we need to remove to make this graph disconnected. That's why edge connectivity equals to 3. Next G5. In G5 we can remove AB, AG, AH. A will be one part, rest will be another part. So here edge connectivity equals to 3. So from this example, we conclude that when G equals to BE is a non-complete connected graph with at least 3 vertices, the minimum degree of vertex of G is an upper bound for both vertex connectivity and edge connectivity. So you can say vertex connectivity and edge connectivity are less than equals to minimum degree. Let's understand this point through this example. Here A degree is 2, G degree is 3, F degree is 3, E degree is 2, D degree is 2, C degree is 3, B degree is 3. Now minimum degree is 2. So for G3, edge connectivity equals to 2. It can be less than or equals to minimum degree. Now check for G4. G4 here degree 3, 3, here 1, 2, 3, 4, 5, 3, 3, 3. In G4, minimum degree is 3. Now check edge connectivity of G4 equals to 3. Now in case of G5, minimum degree is 3. Edge connectivity of G5 equals to 3. So this is a easy way. Just check the minimum degree of that graph, and edge connectivity can be less than or equals to that minimum degree. It will not exceed that minimum degree. Also, another point, vertex connectivity can be less than equals to edge connectivity. In graph 2, vertex connectivity is 1, whereas edge connectivity equals to 2. So vertex connectivity is less than edge connectivity in case of graph 2. We can say K of G is less than equals to gamma of G less than equals to minimum degree. So vertex connectivity can be less than equals to edge connectivity, and that can be less than equals to minimum degree of vertices. Next, application of vertex connectivity and edge connectivity. Here I am just mentioning two applications. There are multiple applications. First, we can use in the network. Like we can model a data network using vertices to represent router and edges to represent link between them. The where how we connect, that are the edges, and router are the vertex. The vertex connectivity of this graph is equals to minimum number of router that we can disconnect when the network is out of service. When the network is out of service, if fewer routers are down, data transmission between every pair of router is still possible. So the edge connectivity represents minimum number of fiber optic links that are down to disconnect the network. So if fewer links are down, it is still possible that data can transmitted between every pair of router. So you can simply disconnect that edges which are not working. In the same way, we are using vertex connectivity and edge connectivity for data network. We can also use for road construction. We can model a highway network using vertices to represent highway intersection and edges to represent the section of the road running between this intersection. So here vertex connectivity means the minimum number of intersection that we can close. In particular, suppose any event time or travel is impossible. So the fewer intersection are closed, travel between every pair of intersection are still possible. Recently there was 4th July parade. So some intersection they closed due to the parade route, right? So whenever required, we can close some intersection, and here edge connectivity means the minimum number of roads that we can close to disconnect the highway network. So if fewer highway are closed, it is possible to travel between any two intersections. You can use this edge connectivity and vertex connectivity to repair the road also. We saw by example how can use vertex connectivity and edge connectivity for data network and highway network. These are just two applications. There are multiple applications of this. In today's lecture, I discussed edge connectivity and application of vertex connectivity and edge connectivity. In next lecture, I will discuss connectedness in directed graph. If this lecture is helpful for you, please like, share and subscribe. Thank you.